Let's now look at a different modality of electron microscopy that we call electron tomography. With electron tomography, we can peer inside the interior of our cells. Like you see in this example, we can view through the cell, we can see all the membranes, how they are arranged inside the cell. We see ribosomes, we see the nuclear envelope, nuclear pores that are associated with that envelope. And from that architectural description, we can understand something about how cells work. Now, how do we arrive at such a 3D reconstruction? We've discussed previously that we can take a set of 2D projection images, for example, of a purified molecule, and work out their relative orientations and use those to derive a three-dimensional reconstruction. This approach, which we call single particle analysis, relies on many copies of identical molecules or objects that are randomly oriented relative to the incident electron radiation. Now, in this case, of course, we cannot use that approach because we only have a unique object that we are observing in projection. We also know that transmission electron microscope images are projection images. And we know from our discussion that a single projection image is insufficient to infer the structure of a 3D object. So how can we then reconstruct a three-dimensional representation of a unique object that we have observed in projection? Now, the answer lies in the following. In single particle analysis, we make use of the fact that we have randomly oriented particles that we can each image individually and then combine all of these projections to get a full coverage of 3D space to get a three-dimensional reconstruction. In tomography, we use a physical orientation of the sample, so we are physically tilting the sample relative to the incident electron radiation, which then combined gives us a set of projection images under different orientations, which we can all combine together to get a 3D reconstruction of a unique object. Now, you may wonder why we not always follow that approach, and it of course comes with a trade-off. In single particle analysis, we can apply the maximum tolerable dose for each of the projection images that we obtain. In tomography, we need to distribute that dose over many projection images that we need to record under different orientations of the object, which means that each of these projection images individually has a lower signal-to-noise ratio. Now let's look at how these projections are relating to the tilted object. We have a phantom image here, and what you can see in this animation is the phantom image rotating, and at the bottom of the screen you see the intensity distribution that we would get from a projection, so a line integral along the incident electron radiation on our detector screen. And as the image is tilted, or the object is tilted, you can see how that projection intensity distribution changes, and each of the different tilts gives us a unique projection image. Now, we can make use of that fact and then construct something that we call a sinogram, that is essentially a radon transform of all the projections that we can obtain from our object of interest. You can see in that animation, as we are tilting our image, each of these tilted images gives us a unique projection that we can add into our sinogram at the relative orientation under which we have observed this projection. Now, similar to the Fourier transform, we can then do the opposite. So once we have recorded this sinogram in our tomography experiment by recording a tilt series of the object of interest, we can take the sinogram and apply an inverse radon transform, and that gives us a reconstruction, a 3D reconstruction that represents the 3D object that we have intentionally imaged. Now, we do that through the process of tomographic reconstruction. So what this implies is that we take each projection that is present in our sinogram and we perform a back projection, so essentially an inverse projection operation. So we are projecting the intensity distribution back across the entire image plane. For each of the orientations, that gives us a back projection slab, and all of these slabs, the back projected lines, intersect in points at which intensity should be adding up in our reconstruction. And you can see that on the far right, where as we are tilting our specimen, so we're moving our way through the sinogram, we're adding more and more unique orientations under which we have observed the object, the reconstruction becomes better and better. Now, the quality of that reconstruction obviously depends on the tilt range, so the angular range that we are covering with our experiment, and the increment of the tilt angle that we are applying. And you can see this in this example. So if we only use a very narrow tilt range of, for example, plus minus 10 degrees, then the reconstruction does not really resemble our original object very well. All information in the direction of the incident beam is still smeared out significantly. But as we are increasing the tilt range, the quality of the reconstruction becomes better and better. And already at plus minus 60 degrees, we get a fair representation of our original 3D object. In addition to the tilt range, it also depends on the tilt increment. So the finer we slice through this sinogram, so the smaller the step sizes, angular step sizes we choose, the better we can represent high resolution detail. And you can see this in this example, where if we use a coarse step size of about 10 degrees, then we also get a relatively coarse reconstruction. But at fine slice step size of 1 degree, we are getting a very finely sampled reconstruction. You also saw from the previous images that even with plus minus 60 degrees, we still seem to be stretching out information in the direction of the incident electron radiation. And that has to do with the fact that because we cannot sample the full tilt range, we are physically limited to about plus minus 70 degrees, we are losing information in the direction along the incident radiation. And we can see that best if we represent our real space images in Fourier space. So we get a Fourier space representation of the real space data. And there we can see that we are missing a wedge of data in that orientation space, which elongates all information perpendicular to that direction. And as the tilt range increases, the missing wedge of information becomes smaller and smaller, and the images become better and better defined. If we could record plus minus 90 degrees, so cover 180 degrees of Fourier space, which is centrosymmetric, so we're covering the entire Fourier sphere, then we would get a reconstruction that should very closely resemble the true image that we are trying to reconstruct. Now, what you've also probably seen is that in our back projection, so the reconstruction that we have obtained from back projecting our sinograms, we obtain an object representation that seems to be blurred. So it seems to be that low resolution information is more abundantly present in these images compared to the sharp original object that we are trying to reconstruct. You can understand that from looking how the back projection actually works. So if we look at a single back projection here, for example, of the specimen at a tilt angle of 0 degrees, which is a certain slice through a sinogram, then you can see that all the projected intensity at that slice is now back projected over the entire image plane. So if we would be reconstructing a single point in real space, we would be back projecting a line in our back projection slab. And we do that for all the different orientations that we have sampled, and that eventually leads to an increase of low resolution frequency or low frequency information in our reconstructed density. In order to mitigate that, we can do something that we call a weighted back projection. So we can represent each of the projection images that are sampled in our sinogram in Fourier space, and then apply a frequency filter to those, where we downweight the low resolution or low frequency information and we upweight the high frequency information. Now, if we apply such a filter to all of our projections and then we do the inverse Fourier transform, we obtain a weighted back projection which now much better reflects the original object in its sharpness.